today's lecture. Hi, everyone, welcome back after the break. So in the first part of lecture today, we learned all about Euler's theorem, which allows you to figure out these large powers even when you're not in a prime modulus. Well, when we were studying roots in modular arithmetic, we used Fermat's little theorem for basically the same kind of thing when you had a prime modulus. And so all we're going to do in this last portion of lecture today is we're going to do the exact same thing, but replace Fermat's little theorem with Euler's theorem and replace the conditions of Fermat's little theorem, the prime modulus and all that, with the conditions of Euler's theorem, that you have the relative primes and all that. So as a reminder, we had Fermat's little theorem for prime p. If a is not congruent to 0 mod p, then a to the p minus 1 is congruent to 1 mod p. And now we have Euler's theorem, which is strictly more powerful. So you don't even need to remember Fermat's little theorem anymore, because you can just always use Euler's theorem wherever you would have used Fermat's little theorem. Where for any number n, if the greatest common divisor of a and n is equal to 1, then a to the phi of n is congruent to 1 mod n, where phi of n is Euler's Totient function, counting the number of relative primes smaller than n. And of course, as I mentioned in the last part of lecture, note that phi of p is equal to p minus 1 for any prime. So if you're in a prime number, Euler's theorem is just Fermat's little theorem. But if you're in a non-prime modulus, then obviously it's different because Fermat's little theorem doesn't apply in non-prime modulus. So how do we find roots? Oh, wrong way. How do we find roots? Well, I mean, we had an algorithm for finding the kth root of a mod p using Fermat's little theorem. What did we do? We had some conditions. So of course you have to start out by checking to make sure that things work. The conditions are that p is prime, a is congruent to 0 mod p, and the greatest common divisor of k and p minus 1 is equal to 1. So k and p minus 1 are relatively prime. And then we also had find 1 as, then what did we do? We found 1 as a combination of k and p minus 1, because that allowed us to say that, that a to the 1 is congruent to a to the km. Okay, so that's what we did for the roots. We rewrote a to the 1 as a to the km. And then once you do that, then finding the kth root is super easy, right? So the kth root of a is just the kth root of a to the km, which is just a to the m mod p. Okay, so now how do we do this using Euler's theorem? Well, let's replace all these pieces with, so instead of Fermat's little theorem, we're going to say Euler's theorem. And instead of mod p, we're going to use mod n, where n is not necessarily a prime. And then instead of a condition that p is prime, we're not going to have that condition at all because n doesn't have to be prime. And then for a not congruent to 0 mod p, instead we're going to replace that with the greatest common divisor of a and n is equal to 1, right? Because that's what you need for Fermat's little theorem. And instead of p minus 1 here, you're going to replace that with phi of n. Okay? So we're going to change our conditions to the conditions of Fermat's of Euler's theorem instead. And then you're going to find 1 as a combination of k, and instead of p minus 1, this will just be phi of n. And everywhere you see p minus 1, you replace that with phi of n. So let me replace that everywhere. Everywhere you see p, replace that with an n. And everything else is the same. So notice that basically all you've done is you replace the condition slightly. So instead of having, you have this new GCD condition, and then you replace p minus 1 everywhere with phi of n. And other than that, this is completely identical, right? So this is the same algorithm, except now we're using the more powerful Euler's theorem instead of Fermat's little theorem. And so it works even for a non-prime modulus under certain conditions of these relative primeness. So typing that all out, basically, it's the same set of conditions, except now the main difference is that our conditions are slightly different. Now we have two relative primeness conditions. You need a to be relatively prime to n, and you need k to be relatively prime to phi of n. And then once that's the case, you do the exact same thing and you get the same answer, the same type of answer. Okay, so let's try it out. So I'm going to try out a relatively easy number first, and then we're going to do a couple of these, and then I'm going to have you do it because problems like this will appear on your final quiz and on your final. So let's take an example. Let's say we have the cube root of 7 mod 10. Okay, so the first thing you're going to do is you're going to check, well, what is phi of 10? Well, phi of 10 is equal to 10 times 1/2 times 4/5. So this is equal to 4. Okay? We already knew that. That's because we've been using mod 10 a couple of times as examples. So phi of 10 is equal to 4. And so then we need to check two things. We need to check, let me do this in different colors. So we need to check that the GCD of A and N, well, what are A and N here? Well, A is 7 and N is 10. Well, the GCD of that is 1, so that's good. But then we also need to check that the GCD of K and phi of N is equal to 1. So GCD of 3 and 4 is equal to 1. Okay, so we're also good. So we meet the conditions of Euler's theorem and using this algorithm. And so we can proceed. So what next? Well, then we just find 1 as a combination of K and phi of N. Well, what's phi of N? Phi of N is, so let's this one here. Well, you can use the Euclidean algorithm. This one's pretty obvious. So 4 is equal to 3 times 1 plus 1. 3 is equal to 3 times 1. You reverse it. 1 is equal to 4 minus 3. Of course, you need to make sure to write it in the same format. So you get 1 is equal to 3 times minus 1 minus 1 times 4. And this here is m. Okay? And then what you do is, well, then you can write this out. Well, km is, that's minus 3, right? Because it's 3 times minus 1. And so here we know that a to the 1, so 7 to the 1, is congruent to 7 to the minus 3, right? And this ought to make sense because we know that 7 to the 4 is congruent to 1, right? By Euler's theorem. This is mod 10. So you know that, and so from that, it ought to make sense that you can subtract 4 from the exponent on both sides, and you get, or sorry, from the exponent 1, and you get 7 to the 1 is congruent to 7 to the minus 3. And well, once you do that, then that means the cube root of 7 is congruent to the cube root of 7 to the minus 3. But 7 to the minus 3 is easy because taking the cube root of that, this is congruent to 7 to the minus 1. Now, there are a couple ways of doing this. So one way of doing this is you could just take the reciprocal now. So you could use the division algorithm, or the other way of doing it, since it's only to the minus 1. But the other way of doing it is you can rewrite this by taking this plus phi of n, because of course you can always add 4 to the exponent in mod 10 for something that's relatively prime. And so then what this is equal to is this is equal to 7 cubed mod 10. Well, and that's congruent to 49 times 7 mod 10, which is congruent to 9 times 7 mod 10, which is congruent to 63, which is congruent to 3 mod 10. And often it's useful to check. So if you're going to check, you can check that 3 cubed is congruent to 27, which is congruent to 7 mod 10. And so 3 is really a cube root of 7 mod 10. Okay, does that make sense to everyone? Okay, great. So let's try it out together. Let's compute the cube root, the fifth root of 3 mod 85. And I'm going to walk this through step by step since it's a lot of different steps. So first, we need to find phi of 85. Which of these numbers is phi of 85? Okay, so it looks like people are starting to get answers. People are getting 64. Well, let's try this out. So 85, oh, I shouldn't be using green. I keep on forgetting that. Let's use orange. So 85, if you do a prime factorization of that, that's 5 and 17. So that's equal to 5 times 17. So then phi of 85 is equal to 85 times 4 over 5 times 16 over 17, which is equal to 64. Okay, great. So that's step one. Step two. Step two. Check if the greatest common divisor of 3 and 85 is equal to 1, and if the greatest common divisor of 5 and the 585 is equal to 1. So I'm just going to do that since so 85 is equal to 3 times 28 plus 1. 3 is equal to 3 times 1, and therefore the GCD of 3 and 85 is equal to 1. And of course, you could also just see that from the prime factorization. Also, well, 64 is equal to 5 times 12 plus 4. 5 is equal to 4 times 1 plus 1. 4 is equal to 4 times 1. And so the GCD of 5 and 64 is equal to 1. Okay, and so since both of these pairs are relatively prime to each other, we're good, right? So that means that we can use the algorithm as we've described it. So what's step 3? What is the value of m? So we need to solve for 1 is equal to km minus L times 5n. What is m? And let me zero out the chat. Okay, so it looks like people are starting to get the answer of m is equal to 13. So, well, let's solve this. So again, we need to use the Euclidean algorithm. 64 is equal to 5 times 12 plus 4. 5 is equal to 4 times 1 plus 1. And so therefore, you could also do 4 is equal to 4 times 1, but therefore we know that 1 is equal to 5 minus 4. And we substitute in 1 is equal to 5 minus 65 times 5 times 12. And so therefore 1 is equal to 5 times 13 minus 64. And together, notice that m is you're multiplying by k. K here is 5. This is k, and this is m. So m is equal to 13. Another way of seeing this is that if you km is equal to 65, and that happens to be equivalent to 3 to the 65 is equivalent to 3 to the 1. But let's keep on going. So let's zero that out. Now we just need to find the answer. And you'll notice while doing this that this in just one problem now, we're forcing you to do all these different steps. And let me just go ahead and write down that the trick is that, of course, 3 is congruent to 3 to the 65, which, of course, means that the fifth root of 3 is congruent to the fifth root of 3 to the 65, which is congruent to 3 to the 13. And that's why m is important. Because from m, you directly know that that's the power you need to take. Looks like we have a couple of answers in chat. Let's wait a little bit longer for everyone to finish computing. Okay, it looks like it's a race between A and B. And it looks like A is ahead, but B is catching up. Okay, well, we've had a number of responses, so let's work this out together. So now, of course, we've used the Euclidean algorithm already. Now instead, we're going to use properties of powers. Let's do this using a binary expansion. And so 3 is congruent to 3. 3 squared is congruent to 9. 3 to the fourth is then congruent to 81. And I'm going to rewrite 81 as minus 4 because that's a little bit easier to square. So because this is all mod 85, so we can do the conversion from positive to negative. And then 3 to the 8 is then going to be congruent to 16. So then we know that 3 to the 13 is congruent to 3 to the 8 times 3 to the 4 times 3, right? So that's 13. So that's congruent to 16 times minus 4 times 3. So this is congruent to minus 64 times 3. Minus 64 is, of course, just 21 times 3. So this is congruent to 63. So the answer is indeed B. Okay, and we have a couple more minutes. So let's solve one all on your own. So instead of going through step by step, now you need to combine all 4 steps together and solve. And this is just one problem. So there will be a problem on the final exam that looks something like this. And it'll just be one problem. So we're actually running out of time. I was hoping to give you guys a little bit more time to solve this since this is sort of a big problem, but since we're running out of time, I'm going to, it looks like we have some answers starting, but let's go ahead and work it out through it together just so that you guys have all of this. So, okay, so we are getting people answering. So, okay, good. Some people are relatively quick. So 521 is equal to 21 times 2/3 times 6/7, which is equal to 12. Then check GCD of 2 and 21 is equal to 1, and the GCD of 5 and 12 is equal to 1. Then you take 12 is equal to 5 times 2 plus 2. 5 is equal to 2 times 2 plus 1. Reverse that. 1 is equal to 5 minus 2 times 2. 1 is equal to 5 minus 12 times 5, 12 minus 5 times 2 times 2. And so then 1 is equal to 5 times 5 minus 12 times 2. Of course, that is correct. So you can double check that. And what you're left with is then, that means that 2 to the 1 is congruent to 2 to the 13, is congruent to 2 to the 25. And you get this, the fifth root of 2 is congruent to 2 to the 5. Because, of course, that was the m that we found here. Okay, so what's 2 to the 5? 2 to the 5 mod 21 is congruent to 32 mod 21, which is congruent to 11 mod 21. And so you end up getting B here. Okay, and with that, I think that will end lecture for today. Next week, we're going to be talking about primality testing as well as codes. And we're going to start talking a little bit about how you can apply all the super esoteric number theory stuff to cryptography and security and banking and things of that sort. So we're going to start talking a little bit more about applications next week. And that's how we're going, after we do primality testing. And that's sort of how we're going to finish out the semester. So yeah, I have office hours at noon. I think that's when I have office hours on Wednesdays. I forget. But whenever I have them posted, I will be in my office then. Oh, no, sorry. I have office hours now. It's Wednesday. So if you have more questions, come and talk to me, and we'll walk over to my office together. So with that, I will see you all on Monday. Bye, everyone. Yep, take care, y'all.